Shallow networks, design, capacity, and learning. Introduction. What is a shallow network? Picture the simplest artificial neural network you could possibly build. No hidden layers, just inputs and a single output, or several outputs working side by side in parallel. That's exactly what's called a shallow network. No deep learning, no stacked layers, just a direct path from input to prediction. You might think that's too simple to be interesting, but it's actually the opposite. Once we understand how a single neuron is designed, how much it can store or learn, and how it's trained efficiently, we've laid the building blocks for everything bigger. In fact, the top layer of any deep network is, at its core, just a shallow network operating on already transformed data. In this video, we'll walk through three big questions. First, how do you design a shallow network in a mathematically principled way, starting from a basic statistical foundation? Second, how much capacity, meaning how much information, can such a network actually hold? And third, how does it learn? And why is learning in shallow networks so well behaved and well understood? The statistical foundation, maximum likelihood. How do you actually decide which error function to use during training and which activation function makes sense at the output? Many textbooks just hand you the answer, but there's a more elegant path. Start from probability theory. Here's the idea. We have a dataset of input-target pairs, say images and their corresponding labels. We assume each data pair is independent of the others. Then we can write the probability of the entire dataset, given the network's weights, as a product of the individual probabilities. That's called the likelihood. To maximize this likelihood, it's computationally more convenient to take the logarithm and flip the sign. That turns a maximization into a minimization, and a product into a sum. The result is an error function we want to minimize. It measures how well the network's output matches the actual target. If we additionally build in an assumption about plausible weights, a so-called prior, we arrive at maximum a posteriori estimation, or MAP for short. That's basically the same idea, except we're also saying some weight combinations are inherently more likely than others. The key insight of this chapter is, depending on which probabilistic model we assume for the targets, Gaussian, binomial, or multinomial, we end up with quite different, but structurally related, error functions. And that's exactly what we'll look at next. Regression, classification, and the one shared formula. Let's look at three concrete cases now: regression, binary classification, and multi-class classification. In regression, the targets are continuous: a price, a temperature. Here, the natural choice is a Gaussian model for the error. Derive the maximum likelihood error function from that, and you land exactly on the good old squared error, the same error function everyone knows from linear regression. Fittingly, we use a linear unit at the output, since the targets aren't confined to a specific range. In binary classification, the target is either 0 or 1. Does this image show a cat or not? A binomial model fits here. The resulting error function is the so-called cross-entropy, which is closely related to the Kullback-Leibler divergence, a measure of how different two probability distributions are. And because the output is interpreted as a probability here, it has to lie between 0 and 1, which is why we use the logistic function, also known as the sigmoid, as the activation. For multi-class classification, more than two categories, we extend this to a multinomial model. The matching activation function is softmax, a generalization of the logistic function that turns a vector of numbers into a probability distribution over all classes. And now for the real payoff of this whole chapter. Whether it's regression, binary, or multi-class classification, if you compute the derivative of the error with respect to a neuron's internal activation, you get the exact same beautifully simple formula in all three cases. The difference between the target and the actual output. That's no coincidence. It's a direct consequence of not choosing the error function and activation function arbitrarily, but deriving them jointly from the same probabilistic model. The result? A single clean learning rule that works for all three problem types. Priors, regularization, and weight decay. Now, for an aspect that's extremely important in practice, what happens when we also build in an assumption about the weights? The most common choice is a zero-mean Gaussian distribution for each individual weight. The idea behind it? Large weights are inherently less likely than small ones. Build that into the MAP estimate, and an extra penalty term shows up in the error function, proportional to the sum of the squared weights. That's called L2 regularization, or in the context of neural networks, weight decay. The weights get nudged a little towards zero at every learning step, on top of the actual gradient step. There are alternatives. L1 regularization penalizes the sum of the absolute values of the weights instead of their squares. That produces an interesting effect. Many weights end up exactly zero, not just small. The network becomes sparse, which can boost interpretability since only a few connections actually stay active. This method is also known as lasso, a technique that originally came from geology and was later popularized for machine learning. An important point: a full Bayesian approach would actually require averaging over the entire distribution of possible weights, rather than just finding a single optimal set of weights. For a single neuron, that's feasible. For large networks, it quickly becomes computationally prohibitive, which is why, in practice, people almost always work with point estimates instead of full Bayesian integration. Probabilistic networks and stochasticity. So far, we've assumed that a network always produces exactly the same output for a given input, fully deterministic. But you can deliberately build randomness in, and that's actually a core tool in modern architectures. You can, for example, add noise right at the input. Each input component is interpreted as the mean of a normal distribution, and you draw a noisy sample from it before feeding it into the network. This boosts robustness and acts like a natural form of data augmentation. Even more interesting is stochasticity in hidden or output layers. For a logistic unit, the output itself can be interpreted as a probability, from which you then actually sample a 1 or a 0, instead of just passing along the continuous value. This exact principle is the core ingredient behind variational autoencoders, one of the most important architectures for generative models. The well-known dropout technique, where units are randomly switched off during training, follows the same underlying idea, deliberately using controlled randomness as a tool rather than treating it merely as noise. Capacity. How much can a shallow network actually learn? Now let's completely shift perspective. Instead of asking how to train, we ask, how many different functions can a single neuron even represent? That's called the capacity of the network. A single linear threshold neuron, you can picture it as a separating plane in space, can implement certain simple logical functions exactly. And, or, not, or, is the majority of the inputs positive? But there are also functions that a single such neuron can never represent exactly, no matter how you adjust the weights. The most famous example is XOR, the exclusive OR. These functions simply aren't linearly separable, no matter how you rotate or shift the separating plane. Here's the exciting question. Out of the unimaginably many possible Boolean functions with n inputs, there are 2 to the power of 2 to the power of n of them. How many can a linear threshold neuron represent? This question was studied for decades and was only fully resolved in the 2000s by the Russian mathematician Zuev. The result is stunningly elegant. Capacity grows roughly like n squared, vastly slower than the astronomical total number of Boolean functions, which grows exponentially as 2 to the power of n. Here's an intuitive way to think about it. A linear threshold neuron is essentially fully determined once you know n bits of information per input dimension, roughly n times n, or n squared bits in total. That information, so to speak, lives in the so-called support vectors, the data points closest to the separating plane. Polynomial boundaries and other neuron types. What happens if, instead of a straight separating plane, we allow a curved, polynomial separating surface? That corresponds exactly to a neuron with a polynomial instead of a linear activation. Capacity then increases noticeably, roughly proportional to n to the power of d plus 1 divided by d factorial, where d is the degree of the polynomial. In other words, the more complex the allowed separating surface, the more distinct functions can be represented, but the capacity gained per additional degree of freedom doesn't grow arbitrarily. It follows a clear mathematical pattern. Other constraints have been studied too. Restrict the weights to just 2 possible values, +1 or -1, and capacity drops dramatically. It then grows only linearly with n instead of quadratically. Allow only positive weights, on the other hand, and capacity surprisingly remains quadratic. And a ReLU neuron, combined with a downstream threshold decision, also has quadratic capacity, structurally similar to the classic linear threshold neuron. Gradient descent and why shallow networks are so well behaved. Let's get to training itself. The standard approach is gradient descent. You nudge each weight a little bit in the direction that shrinks the error the fastest. And because we showed earlier that the derivative for regression and classification always has the same simple form, the difference between target and output, this gives us a single, universal learning rule for all these cases. But the real highlight for shallow networks is this: these error functions are convex. Picture it as the error landscape having the shape of a single, large bowl, with no local valleys the gradient descent could get stuck in. For linear regression, you can even compute the optimum in closed form, exactly, with no iterative training at all, using the covariance matrices of the data. For logistic regression, convexity can also be formally proven by showing that the second derivative, the so-called Hessian matrix, is never negative. This is the fundamental difference from deep networks. There, the error landscape is riddled with countless peaks and valleys, and gradient descent can get stuck in a poor local minimum. For a single shallow neuron or a shallow layer, this problem practically doesn't exist. Gradient descent is guaranteed to find the global optimum. The Perceptron Algorithm. One historical highlight to close things out: the perceptron learning algorithm, one of the oldest learning procedures around. The rule is about as simple as it gets. You start with the weights at 0. Then you go through a misclassified example and shift the weights a bit toward that example if the target was positive, or in the opposite direction if the target was negative. Correctly classified examples are simply ignored. The remarkable part is the so-called perceptron convergence theorem. If the data is separable by a straight plane at all, this simple algorithm is guaranteed to converge in finitely many steps to a perfectly separating plane. The number of steps needed depends on 2 geometric quantities: the radius of the data, and the so-called margin, the smallest distance any point has from the optimal separating plane. The larger that margin, the faster the convergence. If the data isn't separable, on the other hand, the algorithm stays perpetually unstable. But at least the weights themselves don't grow without bound, a result known as the Perceptron cycling theorem. Summary and outlook. Let's recap. Shallow networks might seem simple, but they give us the complete theoretical foundation for everything that follows. We saw that error functions and activation functions aren't chosen arbitrarily, but derived consistently from a probabilistic model. We saw that the capacity of a single neuron is surprisingly precisely quantifiable mathematically, usually quadratic in the number of inputs. And we saw why training shallow networks works so reliably, thanks to convexity, in contrast to the far messier landscape of deep networks. These building blocks, the top layer of a deep network, extreme learning machines with random lower layer weights, or support vector machines, are ultimately all variations on this same shallow principle. In the next video, we'll look at what happens once we add a second trainable layer, and why exactly that step fundamentally changes the error landscape. If this video helped you better understand the foundations of machine learning, feel free to leave a subscribe and let me know in the comments which topic you'd like to see covered in more depth next.